It's some work that I've been doing with Eric Asfog and Alyssa Roden and Joe Spitali and a cast of other characters on the formation of the grooves on Phobos. I'm going to quickly kind of step through just and show how we're modeling stresses on Phobos. I think Eric did a good job yesterday kind of setting up the models that we're using. We're going to then quickly look at the stress from orbital decay and show that many of the grooves kind of fit those tidal stresses. And then something kind of completely new is looking at just the fact that Phobos might be dynamically active right now and how diurnal stresses might actually play out on the surface of Phobos. So first, we use a thin shell model for approximation for calculating the stresses on Phobos. We've built this model and we've tested it against a more rigorous two-layer model, and we find that the thin shell approximation works fairly well and is pretty easy to understand. I can kind of present it to you in a talk and kind of get the basics of it. But basically, the stresses on the surface, the thin elastic outer surface is responding to the tidal deformation of the interior, and this produces stresses on the surface. And you've got two principal components of stress. One that's kind of radial from the axis of symmetry of the tidal deformation, and another principal stress is perpendicular to that along the surface. And so the magnitude of the stresses, not surprisingly, are related to how big a mass is raising the tide on the body, or Mars, and how far away you are from the surface of Mars, or how far away you are from Mars. It also depends on what the rigidity of the outer layer is, and the kind of the density of the object, mostly dominated by the interior, and how well the body can deform due to tides. And so to figure out how well it deforms due to tides, we kind of had to put together a two-layer model based on kind of the work of Sabatini and Vermeersen to calculate how the body deforms due to the tidal gravitational potential for Mars. And so again, we treat this as a two-layer sphere with an average radius of about 11 kilometers. We have it in incompressible layers, and each layer has the same density of about 2 kilograms per meter cubed. The interior, we've used a weaker interior, and the value we use is about 10 to the 6 pascals. This is high enough to support the overburden pressure of the material above the center of Phobos, but it's still a pretty weak material compared to rock, which might be more like 10 to the 9th, 10 to the 10th pascals. The exterior we treat as a layer of about 100 meters thick, and again, that can still kind of approximate thin shell stresses, even that thick layer of 100 meters. And it's more competent with a rigidity of about 10 to the 8th pascals. And we use that, as Eric had mentioned yesterday, we use that value based on analogies to how regolith behaves on the lunar surface based on seismic velocities in the regolith layer. And we find that the tidal response of this body is about 0.02, and that would cause a tide of about 24 meters, a primary tide of about 24 meters. So then we first wanted to look at just what happens as Phobos orbitally decays into Mars. And so because Phobos is orbiting inside the synchronous rotation limit, it's moving faster than Mars is spinning, and it does raise a small tide on Mars, and that tide lags behind Phobos and zaps it from some energy from its orbit slowly, and that as it steals energy, the orbit then decays and gets smaller and smaller until eventually it will hit Mars. And so we calculated the stresses from this orbital decay, and that's what's shown here in the plot on the right. This is just represents the surface of Phobos in longitude and latitude, and we have ticks for the principal stresses at certain locations on the surface. The dark hashes are tension, and the light hashes are compression. We find that the stresses from the orbital decay are on the order of tens of kilopascals, and we think that by analogy to the regolith on the moon and studies of regolith simulants in laboratories here on Earth, that it might fail at something like 1 kilopascal. And so we think that these stresses are large enough to drive fractures in the surface of Phobos. And because of Phobos' small size and the overburden pressure, and mostly because of its small gravity, these stresses can drive cracks down to about 1 kilometer of depth. So then we mapped about 200 features on the surface and compared their orientation to the stress field. And so this is a plot of the results. Again, you can kind of see in the background the hash marks of the tidal stress. Here, yellow is tension and white is compression. I should have mentioned before that in the areas at the sub-Martian point and the anti-Martian point, both principal stresses are in tension, and the interstitial regions have a mix of both compression and tension. When assessing whether or not a fracture is aligned with the tidal stress, we looked at its strike. In the regions on the sub and anti-Martian points, because the stresses are near the isotropic in tension, they're not really diagnostic of an orientation for tidal formation. They're consistent with the tidal formation, but their orientation it may be controlled by something else. So we mostly looked at the interstitial regions, and the fractures here in red are ones that are aligned more perpendicular to the tension, which is indicative that they were formed under tensile failure. And the redder they are, the more closer to 90 degrees perpendicular they are to the tensile tension in the region. And you can see most of the fractures are very closely 90 degrees from the tidal tension. There are a set of grooves over by the Stickney crater that couldn't fit the tidal field, and so they're blue, and they're almost perpendicular or they're actually parallel to the tension and more perpendicular to the compression in that region. And so we would think either these formed at a different time or they're controlled by some other stress. And one thing that we like about the model is that it can actually form different generations of grooves. So here's a plot showing just the orbital distance from Mars along the x-axis and then how far the body has migrated along the y. The points that we were looking at are down here where it's currently located, and it's moved very little to get that tens of pascals. But even if it were further out near the synchronous rotation limit, you wouldn't have to deorbit very far before you get the same level of stresses. So you can imagine that there have been different generations of grooves being formed as the body has migrated in toward Mars. And so now I'd like to talk about stresses from orbital eccentricity, something different. And so because the orbit isn't circular, Mars seems to kind of oscillate above the sky on Phobos. At the 0 degree longitude, 0 degrees latitude, if it were a completely circular orbit, Mars would just hang in the sky right above that point and never move. But because of the eccentricity, the tidal bulge that you're standing on is going to go in and out, pump in and out, so you're going to rise up and down throughout the orbit. And also the location of Mars above you is going to oscillate a few degrees in longitude. And so that constant reworking of the shape of Phobos can also create stresses on the surface. And that's what's shown here in the movie, is that dynamic stress process. Again, this represents the surface of Phobos, and red is tension and blue is compression, and the magnitudes of the stresses are about a quarter of what they were from the orbital infall stresses. But these are very dynamic, and they're changing on the orbital period. And so we think that these kind of stresses can rework, can work on the grooves and kind of keep them active, or if any of them are active, can rework the grooves as they're active. So that's what this movie here shows. And so I'll set this up again. You have the stress field in the background. Red again is tension, and blue is compression, and it's changing throughout the orbital cycle. But now we've kind of assessed what are the stresses on the fractures that we've mapped. And so if the fracture is colored in red, that means that fracture is experiencing tension at that moment. And if it's in blue, it's experiencing compression. And if it's purple, it's actually experiencing a Coulomb failure. So the tension, so it's actually in compression, but the shear stresses are high enough that you could have a failure along the fracture also. And so you can see that the tidal stresses could rework the grooves and cause their stress state to change throughout the orbital cycle. Now, a caution that while I've mapped all 200 features that we've looked at on this plot, it's unlikely that all of them are active at the same time or currently, and probably only one or two might be active at a time. But at least, I think it's quite likely that there might be a young groove that could still be being reworked by the tidal stresses. And so in conclusion, we think that the orbital decay of Phobos can create enough stress to produce the fractures we see on the surface. This isn't a new idea. Soder and Harris kind of proposed it in 1977, but they kind of treated Phobos as a homogeneous sphere, and it's very hard to get high levels of stress under that condition on the surface. And you would take almost all of the migration from the synchronous point to where it is currently to get enough stress to fracture the surface. And then it would just be barely, and it would probably argue that all the grooves formed at the same time. Whereas with the two-layer model, we can produce those stresses, and we can produce those stresses throughout the history of Phobos, leading to many generations of grooves. We find that the interior, in order for this to work, needs to be weaker than the exterior crust. And I think this might be this might be consistent with the formation mechanism of the giant impact, where you're putting together debris in a disk, and it might inherently lead to a weaker body. Plus, it looked like yesterday that Phobos is experiencing a lot of impact as it's accreting its brothers and sisters in orbit. And so that would fracture the interior further and make it weaker. The details of this model are out in JGR online right now, and hopefully in print soon. And then the orbital eccentricity creates a dynamic stress field that might be actively reworking the surface now and causing things that we can detect. And so kind of implications for exploration is that I think we need to kind of get into the idea that maybe Phobos is currently active and it's a dynamic place that we can go and explore now. If you had a laser altimeter, you could probably measure that in and out pumping of the tide, which would be about 1 meter a day. And that would give you constraints on the interior structure. But better yet, if you landed a seismometer on the surface, the reworking of the grooves would produce natural seismic signals that you could then listen for. And so you wouldn't have to wait for an impact. You could just sit there for a few days and get these signals and probe the interior of Phobos with those seismic signals. So with that, I'll take any questions. Thanks.
If, as we heard yesterday, the sticking impact is pretty young, less than 500 million years old, and if it broke the tidal lock and Phobos settled 180 degrees from its original orientation, what effect, if any, would that have on the distribution of the grooves caused by tidal stress?
If it were 180-degree rotation, none, because there's a symmetry around that axis, and that is the long axis. So even if we break the rotation for a little while, it would eventually come back into that formation either this way or 180 degrees.
And if the rotation was, like you said, thousands of years, would that have an effect? Would that kind of amplify what we were talking about, how the moving stresses?
If you were to move, if further out in the orbit, the orbital period controls the diurnal cycle, and so you could have a longer cycle, but it would still be pretty dynamic.
Yeah, just a question. This may be too subtle to pick out, but since it's been 40 years since Viking went to Mars and we got our first pictures of Phobos, has anybody looked at whether or not the grooves have changed visually between those? Maybe too short of a time, the resolution may be too low, but if you're talking about diurnal tides of 1 meter or so, you might get landslides or rapid deformation that you might be able to pick out.
Right, there would be some shaking. I haven't looked at it, and I don't know if the data is, the quality is enough to see really subtle changes.
Okay. Might be something to look at the pictures.
Can I ask a question? Okay. Mars obliquity has changed dramatically over its history, in recent history, as a matter of fact, geologically speaking. So that's obviously going to be driving torques in these satellites as well. And so what effect does does the Mars obliquity change have on the satellites?
I don't know if when it tilts, if it's quick enough that it takes the satellites with it. That would be more a question for Bill or somebody, dynamicist. I don't know what the flopping of the pole would do.
That'd be like putting me on the spot. I don't remember. I don't think the satellites are affected by the pole changes in the orientation of Mars. I don't think they are, but I'd have to go look. I don't remember very well. Does that mean I get to ask my own question? So I better go study that problem. It's a good one. I wanted to ask you, what does it physically mean to have Phobos have sort of a weaker exterior, or sorry, a weaker interior and a strong exterior? At some level, you'd expect that the outside is the one that's getting battered by impacts and the rest, and so I would kind of expect that to be stronger or weaker. But it's kind of the opposite of my expectations. What does that mean?
I think, from what I understand of the way the regolith behaves is as it kind of gets compact, it can kind of create this coherent layer. And it's still fairly weak compared to rock. It's just more competent in the interior.
I can actually answer that.
All right, go ahead.
Oh, well, thank you.
I wrote a paper about this. The idea is that you have smaller particle sizes on the outside, so there's more, it's really the dust that holds these robopiles together, and you just have more interparticle cohesion because the dust is finer on the the regolith is finer on the outside, and you get bigger chunks on the inside, and that's where you have more empty space, and you can create quite a difference that way.
Okay,
I have another question, but I guess we have line over
we have
there,
to
so-
stick to the schedule, I'm sorry.
Okay.
Otherwise, Pascal is going to be...
Discussion.
Okay. And the next speaker is Mihaly Orani with the dust transport